So what? So
All right.
really, I've heard exactly what you said. I've heard that.
Right. So it is time to get started with today's class. I guess I erased the stuff from the other class. This is what we are teaching in 440.
Yeah, I didn't know that. We're doing user problems.
Well, we are dealing with conjunctive normal form resolution and proof by contradiction.
Oh, we're getting proofs by induction sorted.
Kinda.
That's
the symbols.
But we actually proof by contradiction works.
Nope.
Nope. Okay. All right. That's okay. All right. So what we'll do today in this class in cisp310 is actually to go into the processor now. So we are actually going to open up the processor and look at the key components of the processor. And then what we'll do today is really just to look at the pathways between the components and also look at how the music box relates to the processor. So we'll be doing that because I know that the music box is fresh in your mind. So we'll go ahead and start with that first. Okay, so let's go ahead and start with the homework assignment with the music box. And then we'll go from there to into the actual processor. Okay. So we'll take a look at the homework assignment, and of course I cannot remember where I put it. Must be in control unit. All right. So the music box homework assignment has a lot of constraints, and the constraints are there because I want you to design the music box in a special way to match the required mechanism inside the processor. Okay, so that's why I put all those extra constraints, into the music box. And to me, sometimes, solving problems with all of these extra constraints is actually, it trains your thinking pattern. Okay, because if you have, like you can do things any way you want to. It's a creative process. If this were an art class, that probably is a good thing. But this is not an art class. And a lot of times you are given constraints when you are at work. Okay, you're given constraints like you cannot do it this way, you cannot do it that way, for specific reasons that are, that are basically based on what company, what projects you're working on. So working within constraints is actually, something that's really common when you work in industry, especially in programming, designing circuit boards and stuff like that. A lot of times you have to work around constraints. All right, so the constraints here is you can only use one ROM, one register, one adder, one clock signal, which is that square thing with a clock symbol inside, one 7-segment display, one button, one OR gate, one splitter, 2 constants, and any number of wires. I just realized that because you can have a single splitter, but I did not specify how many ways it can split things, and I did not put any limitations of how you can connect the same thing over, to multiple things. This is really a non-constraint completely. Okay, it's just a non-constraint. And in that case, I can say one single constant, and you should still be able to get it to work, because you can start off with a 32-bit constant, right? Use a splitter and split it 32 ways, and then feed it any way you need the zeros and ones in any particular combination. So there's a way to completely cheat out of this particular constraint. Okay, so the constraint on constants and the constraint on one single splitter should be a non-issue at all. Okay, as I was going through this exercise, I was thinking, if I were to defeat the purpose of this homework assignment, but without conflicting with any one of these rules, I just thought of one way to do it. So we'll go ahead and check it out after I give you the proper solution. Then I'll give you the oppositional solution, or the solution of an oppositional student. Me? Okay. All right, so we'll go ahead and check this out and see if we can do it. Okay, so let's get started with Logisim. How many people use evolution for this homework assignment? Okay, so there are at least a few people. Okay, gotcha. I just need to know whether to look for that or not. All right, so we'll go ahead and do it the kind of more traditional way, the correct way. So we'll go ahead and put a ROM module here. We'll have to do something with the ROM module. And then we go to input output, get two of these things because we know we need a button. We also need a 7-segment display. And that should be it. And then in terms of wiring, we know we need one single splitter. And as I said, you can get away with one single constant because I did not limit the width of the constant or the number of bits of that constant. So with one constant, and then we also need a clock signal. So we need to get a clock out of this. And let's see, what else do we need? An OR gate and an adder. Okay, so we need to go to gate, pick out an OR gate, and this has to be a 2-input OR gate. Okay, so we have an OR gate, and then there's one more thing, which is an adder. That's right. Okay, so we go to arithmetic and pick out an adder. There we go. So now we have all the components, and as I said, in the previous company that I worked for, which is like from 1990 to 98, that's a long time ago. This is sometimes how they come up with new products. They just put the parts into a bin, shake it a few times, okay, new product. All right, so now we need to kind of think about what it needs to do. Oh, I'm missing one more thing, the register. Without the register, this is not going to work, right? So register is a part of memory, so we just pick out the register and put it here. And I can do all the configurations later, because the first thing I need to know is how these components are connected. So we know one of the constraints is, or one of the objectives of this design is it has to display from 0 to 9 using the 7-segment display. So the easiest way to generate the 0 to 9 is to have all those binary patterns stored in ROM. Is that making any sense? Okay. So we can kind of say, okay, we just need to make some connections between the ROM and the 7-segment display, and we'll use a splitter. Oh, darn it, we use a splitter over here already, because I can only use one splitter, and this is the way the splitter is going to be used. So I cannot use a splitter for constants. Okay, a single splitter. There we go. I can still do the cheating because I still have the freedom of using any content and any width of the ROM. So I can still kind of cheat my way using a single splitter, but that would be like total abuse of the components. Okay, if I need to do that, I'll do it, but I don't think I need to do that. All right, so we need to split the output into 8 parts is the minimum. If you have 9 bits coming out of the ROM, it's okay, because I did not put a limit of how many wires has to come out of the ROM. Of the 8 wires, I know that 7 of the 8 wires have to go to control the segments, because between the numbers from 0 to 9, 7 segments they all have to be controlled. So I know 7 bits have to go to the 7 segment. So let's see what is the best way to look at this. Okay, this will probably be the best way. So I don't have any overlapping lines and stuff like that. Okay. So this part is kind of boring because it's kind of predictable what I'm doing here. I'm leaving this one alone. And I'll have this one connect to the second last one. And this one over here. And then this one over here. There we go. Okay. The reason why I did not connect the one to the lower right-hand corner is because that one corresponds to the period. And I did not say to light up the period, so the period should not be lit, right? So we'll use a constant to deal with that. All right, so next, what else do we need to do? Well, we need to specify the content of the ROM now, right? Because we need to specify, okay, which 2 segments should light up in order to get a 1, which two segment or which segment should be light up to get a 0, and so on. So to get some help with that, you can go to the library reference, go to input output, go to the 7-segment display, because it shows you the actual wiring, which is really helpful. Okay. So using this wiring, I can just draw it on the whiteboard, and I can say a 0 will involve all of these except for the one here. So it's going to involve so everything except for bit 3. So everything except for bit 3. So we have 1 1 1 0 1 1 1. This is a 7. This is also a 7. So we have a 7 7 for 0 in this case. Now these numbers depend really on how you wire up the ROM to the 7-segment display. If you wire up it differently, then your values will be different. Okay. But in this case, I know this one should work. So I go here and say this is 7 7. Okay. The next one is the 1. So in order to make the 1, I only have 2 segments to turn on, and based on the help file is this one and also this one. So that would be the first and the last bit in this case. So we got 1, and then followed by a bunch of zeros, and then we have 0 0 1 here. So we have 5 zeros in between. So this is a 1, this is a 4. So a 4 1 will correspond to the display of the digit 1 itself. So we'll put a 4 1 over here. Now as we go over this, you can actually test it by just typing in the binary pattern. You can not connect. You basically do not connect to the ROM first. You can connect everything to an input pin. Then you can just play out all the binary bit pattern to find out, okay, is this working before you put it into the ROM. Okay. So this is going to be the 2, and based on the display here, the 2 is going to be this segment here, the second least significant bit. So we have a 1 over here, and then we also have this one turned on, and the middle one has to be turned on.
Yep.
So we got a 0 here, we got a 1 here, and then the next one has to be on, and then this one has to be on, the last one is off. So this is a B. Oops, this is a B because 1 0 1 0 is 10, which is A. This is B, and this one is a 3. So 3B should be corresponding to the 2. So this part is really just reading the diagram and figure out which bit needs to be turned on and which bit needs to be turned off. Then you line up the bits, okay, serially, and then you figure out, okay, what is the hexadecimal representation of those particular bits. So I'm not going to finish the whole thing because that's just kind of boring, right? How much time did it take you to figure out all 10 digits? I mean, the first time you do it's going to be longer than I can do it. It'll be faster. 20 minutes, maybe half an hour, okay? But not much more than that, okay? So this is probably the bulk of the homework assignment is just to do this. So I'm just going to put some random values here. I just have to make sure the most significant bit is off, okay? Other than that, I can just do anything I want. So I can put a 6 4. I can turn on everything for the 8, okay? But this is not 8 itself. Let's just put it back to 8. 0 1 2 3 4. Okay, 8 is right over here. So that's 8. And once we know what is 8, we also what 9 is going to be, because 9 is just missing that 1 here. So 9 is going to be a 1 1 0. So that's going to be a 6. Yep.
7 7 is not 0.
7 7 has all the bits turned on, which is an 8.
At 8. Okay. I thought that one is.
Oh, you're right. Okay, 7 7 because it's 7F, right?
Yes.
Yeah, 7F has everything turned on.
Yeah.
So this one should be 6F. Okay. So the rest I'm just gonna fudge it. I mean, the important part is not that, right? The important part is, how do we connect the rest? Okay, that is the important part. So we'll just go ahead and, just fudge this part. Okay. So it will just, display some Klingon digit and whatnot. Okay, fine, not a problem. Okay. So then, the next thing is to, say, okay, but how do we clock it, right? How do I go from one to the next to the next to the next? Okay. The data lines already used, okay, in order to control, for the most part, the 7-segment display. So we have 2 components here that has to work together. We know the adder is going to be important because the adder is the only component that can quote-unquote increment, okay, but it cannot remember a single thing. You have to constantly give it the input that you're adding, and it'll give you the sum of the inputs. But it has no capacity to remember what was the previous number. There's no such thing as the previous number, right? Okay. So that means, something. Now, the other way to think about this is constraint-based problem solving. Is to look at the adder. You know the adder is going to be useful, and now the question is, how are you going to connect the different pieces into the input pins of the adder? That is the other way to look at this. Okay. We know that we are adding 1. And there are different ways to quote-unquote add 1. How do you add 1 to something? Out of these pins, which ones can you control in order to quote-unquote add 1 to something? You can do it with a carry.
Yeah.
You can also do it with You can also do it with, a carry. You can also do it with the number itself, okay? All right, so I know that I need one more constant, or one constant more than what I really is, what I am allowed to use. So I'm gonna, not cheat, okay? But I'm just going to, fulfill the requirements here. So what I'll do is I'm gonna change the number of bits for the data bits. I'll change it to 9. And I have to change the splitter the same way. So now it's a 9-way split, like that. And I have 1 extra wire that should be not connected now. Okay, this one is still not connected. So there should be 1 extra, okay, it's using this one. So that means I have to redraw that part quite a bit in order to make it work. That's okay. It's not letting me select just that wire. Okay, let's see if this works. Nope. All right, fine.
You can try extending it.
Hmm?
You can try extending it and then deleting it.
Oh, okay. Move it around first.
No, extend the wire.
Extend the wire. Oh, attach something else to it?
Or just make it longer in the same direction and then delete it.
That, okay.
If you click the wire and then shift click the splitter, it'll select the splitter.
Say again?
You click the wire,
Uh-huh.
shift click the splitter, it'll unselect the splitter.
Oh, undeselected. Okay, I see. So you can deselect the portion that you don't want to select. Okay, great idea. Thank you. All right. Oh, this does require me to redraw a good portion of that. It's okay. It's the same way when you're designing a circuit board. It really is, tedious when you need to change the wiring, especially after you have all the traces already determined. It is just a pain to do all that. Now I'm doing this because I don't want to.
I think you should just period.
Yeah, I think we're good.
Yep.
Yep, we're good. There we go. We're good. This is fine. Because all of these have the most significant being 0, so the period will remain off, for all 10 digits. Okay, not a problem. See, this is how you can fudge the design and basically have any constant you want, because you just make the ROM wider and then make all the locations have exactly the same bits for all the clock cycles. Okay, so now the deal with that part is done. Okay, so let's go back and zoom out, because the focus now is what about the register and the adder? Okay, the register is the only component in this picture that can remember something. Okay, and the adder is the only component here that can actually add 1 to the input values. So you have to combine these two in order to add 1 to the value of the register itself. Okay. So we already know, based on these constraints, we already know that one of the things that we have to connect between these two is the output of the register has to be one of the inputs. Now, which one, it doesn't really matter, because addition is commutative. So you can use either one. Doesn't really matter which one you use. Okay. So we'll just pick out the top one. Now you have to decide whether to put a 0 here and then specify a 1 here, or vice versa, because you can also do it in a different, in vice versa way. Okay, but you only have 2 constants, and there are other components that will require a constant of 1, because you need the register to be always enabled. That needs a 1. You need the ROM to be always enabled. That needs a 1, right? And those are single bit 1s. If I were to only use a single bit 1 and try to reuse that bit as many times as I possibly can, that will be the constant 1, okay, as a 1 single bit. So this 1 single bit here is going to be reused a few times, because I can use it over here to basically specify the ROM is always enabled. I can attach it here to basically specify the register is always on, or always enabled. In other words, it is always ready to be updated, but it is still, oh, this is the clock line. This is the enable. Here we go. Okay, and let's see, what else do we need to use the 1? We can use a 1 for carry in, because carry in is just one extra thing for the adder to add. In other words, the adder is adding 3 components. It's adding the input carry and also the 2 numbers that you're feeding to it. Now, have we seen the adder like this before? Remember your adder homework assignment? It has got to carry in, right?
Yeah.
So that carry in serves exactly the same purpose as this particular carry in. It's just one extra component that we can specify for adding. So we are reusing this one bit of 1 here quite a few times. And then the other thing is, okay, what do we specify over here? We have to specify a 0. But that 0 is going to be a multi-bit 0. Whatever the width of the adder is, has to be the width of that 0. So this is a good time to review, okay, do we really need 8 bits for the adder? Do we need 8 bits for the register? Because the input of the address of the ROM, do we need 8 bits over here? The answer is we don't, okay, but can we use 8 bits? Sure we can, because you don't need 8 bits to count up to 10, but if you specify 8 bits, well, you can still count to 10. So if you want to keep the default and just keep it fixed to 8 bits, it's fine, okay? I did not ask for optimization and use the least number of locations in ROM, so you can keep it as an 8-bit address bus, no problem. Okay, so that means our constant 0 has to be an 8-bit 0. So we go to constant, and this time we specify it has 8 bits, and together it specifies 0. Okay, there we go. We now have a 0 constant as the other number. Okay, so now we have the register connected to the adder, and then the output of the adder obviously is significant. Otherwise, why would I put an adder here if I ignore the output of the adder? So the question now is, where do I connect the output of the adder? You can hook it up to the address of ROM, but I would put it back into D of the register. So something has to go back to the input of the register, and I'm just going to take the output of the adder and put it back into the input of the register. So this means, if I have a clock transition, then the register will now be updated based on the output of the adder, right? But the output of the adder is 1 added to the current value of the register. But it seems like we have a problem. So now that the register is updated, wouldn't the new value of the register be output at Q, and then the adder will add 1 to that, and then go back and keep adding, so it's not going to stop. Well, there's one thing that will guard from this loop to happen. What is that? The clock line, because the register is edge sensitive. It will only update the content when you have a rising edge from 0 to 1 on the clock line. And that's why it won't be stuck in an infinite loop all by itself. It is all controlled by the clock. Oh, I missed one more because I need this to be a 0. Oh, I have a 1 here. I can't hook it up here. Oh, I can cheat. I know where I can get a 0. Something in this picture should be a 0 all the time. I can pick out the 0 from the ROM. Yeah, I can do that. That's actually another 0 that's always going to be a 0, but it's kind of like really, it's really a kludge. It's so much of a kludge that I really don't want to use it. This is always a 0. we never overflow the adder, so the carry out of the adder is always a constant 0. So I could have used that as a 0 bit.
Why not just use the constant?
I can only use 2 constants.
Well, you already have a 0 constant, but is the bit size?
It's a multi-bit constant, but I can only use 1 splitter, so I can't split that multi-bit constant into individual zeros. But you can see how constraint can kind of really. Okay, this is what thinking out of the box is about. Okay. What is the box? Where's the box? Who put a box on our head? We did. Okay? That box was put on our own head because we think, oh, in order to get a 0, it has to be a constant. We have to make a constant 0. Okay? But in reality, we can use one of these components to make a constant of 0, given the constraint of the homework assignment. We'll still be able to get a constant 0, out of the other components. So that's what thinking out of the box is about, is to get out of the assumption and say that, oh, we can only get a 0 because there's a constant. No, the other things can give you a constant of 0 too. The question is, how do you make those things to give you a constant of 0? Okay. All right, so since this one is always a 0, I will just go ahead and use that. Okay, because I need to make sure that the register doesn't reset by itself. Oh wait, I don't want to do this, because sometimes I do want it to reset, right? Okay. I forgot about that part of the homework. Okay, so we do want it to reset by itself sometimes, but for this particular demonstration, let's just say that I don't want it to reset to 0, because I just want to see the clocking and this part work. Okay, so that's all I need. So right now, this is not complete. This design is incomplete. But what I do, we need a clock over here. But what I do want to show is, okay, we have a mechanism to increment the address, and then the address will control which location is addressed, and then the display will go up. Okay, now, can it go back to 0? Well, we'll worry about that later, okay? Because right now my concern is, well, can I make it work first? Okay, can this mechanism work? So we'll go to simulate, and then we can always just Control T for individual clocks. Okay, so Control T. Okay, so we got it working, even though some of the numbers are not actual digits. But I do get it to work, but I cannot get it to go back to 0. But that's okay, because we haven't touched that part of the design just yet. Are there any questions about the design up to this point, where we have a mechanism to count and basically use that as an index into the ROM, and then use the ROM output to basically control the 7-segment display and to supply us that constant 0 bit? Any questions about this part? Okay. All right, so the next experiment I want to run is to say, I know we need a button to be able to control the reset of this whole thing. So let's get rid of this line here, because I don't want a constant 0 to go into here. Instead, I want the button to help me control whether I want it to go back to 0 or not. Okay. So now we'll go ahead and simulate again. Control T, and I'll press the button. Oops, change to the tool. Okay. There we go. So you can see how you're pressing the button, immediately reset the register, and that changes the address back to 0. So now we're counting from the beginning again. That works. Okay, very good. So we are pretty close to the solution. We're only missing one part. There's no way for me to go to the end and reset the whole thing back to 0 automatically. I can do it by hand, but I can't do it automatically. So what are the constraints now? What we want to do is to reset back to 0. So we know that we need a second way to put a 1 into the 0 pin of the register. We know that's probably a proper way of doing that. We know there's one component that is not used yet, the OR gate. And we also know the OR gate has a property of if any one of the input is a 1, the output is going to be a 1. So it's a perfect mechanism to combine two different ways of resetting the counter into one single input into the register itself. Is that okay? So then we say, okay, we can now say this is now not connected. Okay, disconnect this one, and instead we'll use the output of the OR gate to control the reset of the register. And we know one of the input into the OR gate is going to be the button, because whenever we press the button, we want the register to reset to 0. Okay, so now we want to say, okay, what about the automatic way to reset to 0? How do we make the mechanism automatically restart from 0 once we have counted up to 9? Hey, we got two wires, or one wire that is dangling, that has nowhere to go at this point, and it is controlled by the content of ROM. We're talking about this wire specifically. Okay? And the content, or when this wire becomes a 1, who controls that? The ROM, or the content of ROM, controls this wire. So that means if you specify certain values in certain locations in the ROM, you can control when this wire becomes a 1, and as a result, it's going to go back to the register and then reset the register to 0. Is that okay? But how do we control that? When do we want this to be a 1? After we have counted all the way, after we display the 9, which means location A is the one that needs to set this wire to a 1. So we look at the content of the ROM, we go to location A, which is this one here, and we want to set it to a 1. So in this case, because I added that extra constant 0 here, this is going to be 100. The 1 of the 100 specifies bit 8 to be a 1. Okay. So now we have that specified. This is the other way to reset the register. So it becomes the other input into the OR gate, and that is the complete design. And I think this design meets all the requirements of the homework assignment. It only uses the component that is allowed to be used, including the constants and the splitter and and everything else. Okay, let's run it. Make sure it works, right? If I don't run it, there's a chance that it may not work. So we'll go ahead and take. Yeah, that's a little too fast. So we change the tick frequency to 8 Hertz. There we go. That reminds me of a Star Trek movie where the Klingons they made a time bomb, and just like all the time bombs, it has to display the number, the countdown number, and also beep at the same time. Yep. So, are there any questions about the music box homework assignment? Yep.
There are many different ways to implement this, right? Not just how we won't be taking points off. It's not the same as yours.
Okay, so the grading criteria is based on the description of the homework. So the homework description says, to make a music box like this, you will need and only use the following components in Logic Sim. So if you use additional components, that's not going to be following the constraints. But if you use exactly only these components and get it done, I mean, sure, I mean, that works. Yeah. Mm-hmm.
What about another constant for the zero that you?
I think I said in class that you can use any number of constants, so so that requirement is going to be relaxed because of what I said. Yep.
I know you, but you never got back to me. I just want to know, so you can use tunnels?
Tunnels?
Just to clean up the lines?
Yes, you can use tunnels to clean up the design because tunnels don't really buy you anything. You know.
Mine works just fine, but I use tunnels just because
Yeah.
it was neater.
Yeah, it makes it look neater because you don't have wires flying all over the place.
Yeah.
Yep, yep. So tunnels are fine. Any other questions about this one?
You didn't like the ball like that. That seems that it's like sounds like this way. Good things.
Oh, not all the pins are connected.
Like period.
I didn't specify it in the assignment, but I did say in class. So it works the other way around this time. In general, it's not a good idea to leave input pins unconnected. And I understand an LED is a heavy load, so if it's not connected, it's not gonna, because of transient signal, it's not gonna light up, by itself. So I'm gonna let that go. So if you leave anything unconnected to the 7-segment display, I'm not gonna take any points off. But in practice, that in general, you don't want to leave any input pins unconnected. All right. Any other questions? See, this is one good thing about recording is if I mark something wrong and I take points off, but earlier in class I said it's okay, you can use any number of blah blah blah. They can always point back and say, hey, the video on this particular day, at this particular segment, you specifically said it's okay to use any number of blah blah blah. So it works to your advantage sometimes too. Truth does not take sides, right? All right, so that's your homework assignment. And we are going to see this again in the processor. Okay, so if there are no questions about the homework assignment, then we're going to move on to the processor. So we'll go ahead and close this. Okay, there we go. Actually, I want to open the processor first and then close this so I don't have to reopen it. There we go. So this is the processor. And I was kind of hoping that somebody would say, but Tech, you got this mechanism already, implemented. I just had to copy it. But nobody said anything, so I was kind of like, okay. I mean, that's your music box, right? It looks a little bit more complicated. It is more complicated, but it is your music box. This is the ROM, right? This is the adder. This is the register controlling the adder. The clock signal goes into the clock, and then you have the constant of 1 to always enable the register, and also to specify a 1 to add. There's a constant of 0, and also an OR gate to control the reset of the register. And the OR gate in this case, one connects to the reset line, which is a global reset line of the entire processor. And guess where the other one is connected to? Back to the ROM. In other words, I'm pretty sure I displayed the processor at least once in this class. But I didn't mention anything about, oh, guess what? Your homework assignment is actually in the processor already. But that's why you're doing your homework assignment. That's why you have your music box homework assignment, because you are using that as a very important component of the processor. This part here, okay, if you look at this part, this is called the microcode engine of a processor. You can look at this as the conductor of the processor, whereas the rest, the other components are, this is the violin section, this is the flute section, this is the cello section, and so on. This is the conductor. This is the guy who's in charge of orchestrating how all the other components work. Okay, that's important. This is really important because this is the one engine that keeps everything else coordinated. So now we move to focus on different things. Okay, look at things that we have already talked about. This is your register bank. Yep.
Sorry, just a little sidebar. It's about the register that you had at the bottom, where it's labeled Ucode pointer.
Mhm.
How it has the 3 zeros on the inside. Is that just like it can go up to a higher value? Is that
Yes.
Oh, okay.
It has to do with this ROM has a 12-bit address bus, so it has got 4,096 locations, and that's why we need one more digit in order to control that many locations.
Oh, okay.
Yep. Okay, but that's a good question. Okay, I didn't show you the cheat where you don't need an OR gate to reset the counter. Does anyone want to know how that works? Sure, why not, right? Okay. Okay, so that cheat has to do with this. This is the adder. So you have one input, you have the other input. So what you do is you hook up the register, the queue of the register to both of these. And then you specify a 0 for the carry in. So what we're really doing is effectively we are doubling the value of the register for each clock cycle. So you have the same clock, this is still going to the clock. The reset line is still, the reset line in this case only has to go to the button. You don't need anything back from the ROM to do this, okay? And let's see, would that work? It's not gonna work. Shucks. It is not going to work because there's no way to go from 0 to 1 because I'm counting it go from 1 to 2, 2 to 4, 4 to 8. So this way I can control the number of width, the width of the address bus in order for the whole thing to reset all by itself. But I can't do that because I cannot go from 0 to 1. Darn it. Okay, so it won't work. Never mind. Okay, so getting back to this one, getting back to this design here. So we have talked about some of these components already. This is the register bank. If you right click and say view register bank, this is something that should look familiar because we just talked about this in the previous class. Okay? And if you look at the other one, if you go back to main and you look at this box here, this is our ALU. And we have seen the ALU already. Okay, I explained the operation of the ALU, the class before we talk about the register bank. But how do we get the values into the ALU to compute the sum of something or the difference of something and store the value of the calculation back into a register? That becomes the next question. So what do you think? How do we figure out, okay, if I want to add the value of one register to the value of another register and then store it back to one of those two registers, what do I need to do? Looking at this picture. So we start off with the source of the data, right? Okay, this is one of the registers. Okay, it is the output of one of the 4 registers. This is the output of one of the 4 registers as well. But you can see that none of these two connect to the ALU directly because the ALU is over here. Each one is going through a demux. So what you need to do is to go through the demux and figure out which wire of the demux is needed. And that is going to be specified by this particular signal here. That's the selection signal. And then likewise, the out one is connected to this demux. We want this wire to be active, to be connected to the input. So you have to specify a 1, in this case, for the demux selection, for this particular demux. Does it make sense? And what about this guy having the enable? So that means the enable also has to be a 1 in order for the demux to actually drive the line going into the ALU. So that means when you look at this picture, there are multiple components that need to work together in order to get 2 registers out of the register bank and connect those registers into the input of the ALU. Good. Now that we have the registers connected to the ALU, what are we doing with the ALU, right? What kind of operation are we doing? So when you look at the ALU, okay, when you look at the details of the ALU, you can see that this is one input, this is another input. Okay, great. We got these already connected. But we also have to make sure that the ALU itself is enabled. This is ALU enabled signal, and that is connected to many, many different components, including the two main demuxes and also the final mux that output something out of the ALU. So that has to be a 1 in order for the ALU to be functional. And then one more thing we also need to specify is operation selection, which is this wire here, because it also feeds to all of the demuxes and also the 1-0 mux, because that is going to specify what operation are we performing. Are we adding, are we subtracting, are we bit shifting, or what? So from the outside view, we also have the output of the ALU, which is this one here, and also the flags, which is represented by this part over here. So when you get back into the design, when you get back into the main design, this is what we need to do is we also have to specify what is ALU enable, okay? Because if we want to do something with the ALU enable has to be a 1. We have to specify the selection signal to specify are we adding, are we subtracting, and this one has to be 0, 0, 0 is a addition, 0, 0, 1 is a subtraction, and so on. So to understand which number is specifying which operation, it depends on how the muxes and the demuxes work inside the ALU. So are we doing okay so far with the operation? All these different things that we have to coordinate just to get 2 numbers out of the register bank to perform the add operation. After we do the add operation, you probably want to store the sum somewhere, right? So that means this wire needs to eventually connect to something that can store something. But you can see that this wire is only going into a single mux. And this mux eventually feeds into the input into the register bank. So that means we have to use the selection for this mux to specify this wire is going to connect to the output. And we also have to enable the mux in order to specify, yes, go ahead and output something into this input here. And then in the register, for the register bank, we have to specify which register is going to store the value out of the ALU. And then the clock is the one that needs to have a rising edge in order for the new value to be stored in one of the registers in the register bank. So what seems to us to be, oh, we are just adding 2 values, 2 registers, get the value, and put it back into one single register. A lot of things have to happen in order for that to occur. So who's orchestrating all of these things? Who's controlling, RI cell? Let me just point out which ones I'm talking about here. So who's coordinating, RI cell, RI in, RI mugs? This one doesn't have a name, but it's out 0. Well, this one is not specified, but this one is. This is R0, RO0 select, RO0 enable, and so on. Who's in charge of controlling those bits? Yep.
It's the ROM.
It's the ROM, because these are all tunnels, right? So one really nice thing about LogicSim is when you click on a wire, it will highlight everything that is logically connected to that wire. So in this case, RO, which stands for Register Output 0 Enable, you can see it is also connected here, which goes into a splitter that eventually connects to ucode data. And ucode data, this wire, is eventually connected to the ROM. So the ROM, in other words, the ROM of your music box is the one component that is connecting and coordinating all of the other components in the processor in order to get things done. Do we have any questions at this point? No questions? Yep.
So the instructions that are stored in the ROM, those can be overwritten.
They cannot be overwritten by this mechanism itself because it's read-only memory. In other words, once you specify the content of the ROM in an actual processor, they stay the same all the time. They cannot be overwritten. Okay. Yep.
So what part of the computer would send the message, say, like add 2 numbers and store them in memory?
Okay, that's a very good question. So the question is, which part of the computer is going to specify I need to add 2 numbers? And by the way, I want register A and register B to be the register supplying the values, and I want the result to be stored back into register A. That's what you're asking, right? So what is specifying those operations? Okay, very good. So what we need to do now is to say, okay, who is controlling the address line of the ROM? Okay, I just highlighted, the wire, and not surprisingly, it's controlled by the register. Just like your music box has its own register, stepping up and incrementing, controlling the address line. So that part is not really surprising. The question is, how do we initialize the value of ucode pointer? Now, in your homework assignment, there's only one way to initialize the register, which is pressing the button. Okay? But in this case, there are 2 ways to specify the value of the register. Let's take a look at the input into the register. So let me kind of bump up the zoom here, because this way we can look a little bit closer to the circuit. Okay, there we go. So this is our register. This is the output. We know the output connects to the address line of the ROM, so that when we increment the microcode pointer, we'll point to the next one, point to the next one. So the conductor is basically waving the, how do you call that thing? The baton, so that the rest of the processor knows what to do. But the question is, how do we initialize, or how do we specify the value going into the register? We can see that this is not simple like your homework assignment. Your homework assignment only connects the input of the register to the output of the adder. But in this case, it is going through a mux, which means we have 2 ways to specify what is the new value of the microcode pointer. One way is similar to what you do, okay? If you look at this wire here, it is connecting from the output of the adder back to the mux, and the mux connects it to the input of the register. So if I choose this way, then it's the same thing as your homework assignment. It simply goes to the next location, the next location, the next location, as we have rising edges of the clock. Okay? What about that other wire? Where is that coming from? That other wire is coming from a merger, okay? Basically it's a splitter, but seen in a reverse way. So when you look at this merger, okay, when you look at this particular merger, the numbers on the merger, on the smaller branches, it tells you how the individual bits are specified to become that one input into the mux. Okay? So in this case, it is specifying bit 0 to bit 3 are all zeros. It's a constant. Okay? And that forms the least significant 4 bits. So you basically say, okay, the input into input 0 of the mux would have 4 zeros as the least significant bits for sure, because those are constants. What about the other wires? What about bit 4 to bit 14? This is bit 4. This is bit 8. And bit 11 is the last one, is the most significant bit. Where do these bits come from? Okay. So in order to find that out, we have to look at instruction. Okay, so we highlight instruction, and then we say, okay, where is that connected to? It is connected here. So it's connected here, which means it is coming from the instruction register. So now our question becomes, okay, so who is going to specify the content of the instruction register? So we know this is coming from the instruction register. But now the question is, who is controlling, who's specifying the value inside the instruction register? What do you think? So we have to zoom out a little bit because we want to see how this D line, how this D port is connected. So we have to zoom out a little bit, okay? And scroll a little bit here. And what do you see? It comes from RAM. And what kind of architecture is this that we are? It seems like we have the ability to store instructions in memory. And what is the name of this architecture? Von Neumann. Exactly. This is the heart, or this is the reason why we have von Neumann architecture. We can read instructions, or we can read individual bytes or memory content in general from RAM and use it to specify what we need to do based on that particular bit pattern. Is that making any sense or not? Yep.
So with the program, it would be compiled down to machine language and stored in memory, and then when you want to run it, it gets pulled into RAM, and the RAM executes on the processor.
Each instruction, each opcode that you store in RAM will feed into the instruction register. Let me just point out here. So each instruction in RAM would get pulled into the instruction register. The instruction register will feed into this mechanism here in order to initialize the microcode pointer. Once you initialize the microcode pointer, the ROM corresponding to the microcode section has, well, okay, this one is not loaded with those values yet. Oh, it is. So it is loaded with these values, and those particular bit patterns is going to specify, is going to orchestrate the rest of the processor to add, to subtract, to do indirect access, to store something back into RAM, to read something from RAM, and so on. So that's the whole picture. Are there any questions about this? Well, can we see it actually working, right? I mean, how do we do this? So in this class, I'm just going to give you an overview, and then we'll go ahead and actually take a more closer look at things. Okay. So what we'll do is we will explore some of the instructions, and all of this is on the shared drive already. So when you go use a browser and go to the shared drive, let me see if I have that already here. Yep. So this is the shared drive. You have access to this already. You go to the processor, and there's a manual for the instructions. So the instruction manual is called Assembler Manual, which describes how to work with the toy processor. And these are the instructions that you can specify. So we can add two registers. We can subtract a value of one register from another register. So let me just kind of take a step back and explain how to read this. Okay. This is called a mnemonics of an instruction. A mnemonic of an instruction is really a name that is easy for us to remember. Okay, mnemonics spells as M-N-E-M-O-N-I-C, mnemonic. The M is silent. But it really is just an easy way for us to remember what the instruction does. The other side, which is this part here, is the best way to describe it in C++ constructs. Okay, so when the halt instruction executes, it is stuck in an infinite loop. It will not exit, and that's the end of everything. Your execution reaches an end, and it won't move forward any further. The no op instruction is basically just doing nothing. And then we have the add instruction. Now with the add instruction, you have to be careful because it takes two operands only, which means one of the operand is going to store the result as well. So in this case, the C syntax is specifying x plus equal to y, which is the same thing as x equals x plus y. So whatever you specify as x is also going to store the value of the sum. It will supply value to add, but it will also store the value of the sum. Subtraction, same thing. X is the one that will store the difference. Compare is the same thing as just x minus y without the equal. In other words, it will go through the very same motion as subtraction, but it doesn't store the result anywhere. The flags, on the other hand, will still be set exactly the same way as a normal subtraction. Okay? So that's basically how we do compare. The AND operation is going to perform a bitwise AND and store the result back into X. This is bitwise OR, same thing. The result is stored in X. This is negation of X, okay? And this is right shifting X by Y bits, okay? Which is the same thing as X equals to X right shift by Y bits. Are there any questions about these particular operations? And by the way, in this case, X and Y can only be registers, and there are 4 registers in the register bank. The registers must be named A, B, C, D. So you have register A, register B, register C, and register D. X can be any one of those 4, Y can be any one of those 4. Is that okay? All right. Let's just play with these a little bit, okay? So what we'll do is we are going to go back to the processor. Well, not yet, okay? We have to assemble this program first. This is what you can see and what you can remember. Do you think if I just type ADD X, Y somehow into the processor, it knows what to do? How is ADD represented as the way we see it? Yep, go ahead.
Another question.
Can you describe what the right shift does?
Right shift is this operator in C, which means it moves the individual bits to the right-hand side. So if I have X right shift Y, that means Y as a number specifies the number of bit position that each bit of X is going to move to the right-hand side. Okay. All right. So we'll go ahead and then the next thing we need to do is to figure out, okay, so this is how we can remember, this is how we can specify the instructions, but what is the processor actually going to see when we say add register A to register B, okay? This is where the assembler comes in handy. This is an assembler, but it is written as a spreadsheet. Okay, so I'll delete what I already have here. So we'll go ahead and specify just that one thing. So we're going to say add, and since I don't believe what tech has written as in the manual, I'm going to say I want to add 1 to A, a constant 1 to A, which is just incrementing the value of register A. Okay, and I don't think anything bad is going to happen. Okay, so we'll see whether something bad is going to happen or not. Press the enter key, and column B says what? Register Y expected, because what is taking the place of Y is not a register. In other words, this assembler, even though it's written as a spreadsheet, does have a certain degree of syntax checking. You have to give it a register. Okay, so if I change the 1 to a B to B, it's going to be okay. Then the syntax error goes away. So what do we do now? Okay. If you really want to look into the mnemonics and what is the actual opcode of each individual instruction, this is the slide you want to look. Okay, you may not want to. We'll get to this later. Okay, I want to give you a feel of overall what it is going to do, and then this one is even crazier because it's using spreadsheet functions to break this string into individual parts, and then use the individual parts to figure out what is the actual code that will come out as the opcode. So for the most part, you really only want to know this, which is the output file that you need to save in order to, this is what you can do to import into Logisim so they can specify the content of RAM. Okay? So let's go ahead and complete one transaction here. So we look at this and say, okay, go to File, and then you say download as, and this is what you need. You want to download it as a comma separated value file, CSV. The actual name does not really matter. Okay, so we'll go ahead and save it into the temp folder, and I'll give it a name of just add, okay, because that's what it's doing. If you really want to emphasize this is intended as RAM content of your Logisim processor, just change the extension to RAM just so that you remember what it is for, okay? Because otherwise you look at CSV and you may not remember what it's for. So I usually just change it to RAM just so that I remember what it's for. Click Save, and now we have that file saved. So the first thing I want to do is to take a look at that file and go like, okay, what is special about that file? So we'll take a look at add.ram in my temp folder, and you say, is there anything special about this file? It looks exactly the same as what we saw in the spreadsheet. Exactly the same. Okay, let me just do it side by side. They're exactly the same. Okay? All right. So then what we'll do is we are going to have Logisim to read this file. So let me go back to, okay, I'm going to close the ones that I don't need. We don't need this. And we don't need that. It's still ticking. It hasn't exploded yet. Okay, so now we can go back here, and then we go to the RAM module, and then we do a right click. Well, before we do that, okay, this is important, because you want to do a reset before you do anything else, because you want to reset the processor back to the reset state before you start the execution of a program. So that's kind of important. Then you right click on the RAM module, and then you say load image. And this is where you can specify that file in the temp folder, and it's called add.ram. Click open, and you can see 8.1 is now in this file. Now, you guys would say, attack, it will take you far less time to just type 8.1 in the RAM. Well, that might be the case in this case, but when your program has like 30 or 40 bytes and they're all hexadecimal digits, this might be faster. Okay, just save the file and then load it into the RAM module instead of hand copying everything. Okay, so we are ready to run the program, but this program is not going to have any visual result because the registers do not have anything to begin with. So what I'll do next is to go into the register and give it some values. So I'll go here and then I look at the first register, register A. We'll give it a value of 10 in hexadecimal, and then register B is going to have an initial value of 20 to begin with. So this way I'm adding some non-zero values. I can actually tell whether the instruction works or not. Okay, and then we go back to the main board here. So now we are ready to run the program. We are actually ready to run the single instruction that is stored in RAM. Yep.
Is there a command to actually, like, or when we put instructions into RAM, is there an instruction we can have to set a register to a specific value? Or do we have
Yes, there is an instruction to read the next RAM location into a register. This is, okay, this processor is close to as risky as it gets, okay? In other words, this is as minimalist as it possibly can, close to. I do have some features that are not exactly minimalist, but they are just convenient to have. Okay, so we are ready to run this program. Now to run this program, if you want to look at what is being changed and whatnot, one thing you can possibly do is to go to simulate and go to logging. And in logging, if you're interested in the flags and see how they are changing as you execute the program, you can just click it and add to the log file. If you're interested to know how the microcode pointer is changing, add it to the stuff that you're logging. For ALU and register bank, if you want to look at register A, add it. If you want to look at anything specific, you can always do that. If you want to look at the program counter, add it to the log list as well. So this is one way you can. It really helps you to understand when you execute an instruction, what is actually going on. Okay, because it allows you to probe and log individual components and save it as a text file. Then you can just annotate the text file once you have the text file. Okay, so we'll close this window. And by the way, if you want to save it as a text file, you want to go to File and specify what file you want to use. Otherwise, it is saved in memory only, so you can see it, but it's not in the file. All right. So everything starts off with this pattern. You can see it is already selected. And so instead of just blindly executing the microcode, and just go like, oh, I can see this is just adding the two integers or the two registers. One thing you might want to do is just do it once or twice, okay? Is to decode this particular bit pattern and see how it is actually actuating the various components of the processor. Yes, it is a lot of work because you're looking at a 7-digit hexadecimal numbers. So how many bits does it translate to? 20 something. Okay, it may not be exactly 28 because the most significant bit, the most significant hexadecimal number, I think it only alternates between a 0 and a 1. So I think it is really just 6 times 4, which is 24, plus 1, which is 25. So I think it really only has 20, no, I lied. It has got 26 bits as the output because this is 25. So bit 0 to bit 25 means we have 26 bits coming out of it. But once you do the translation, then you can see how it is doing the work. Okay, because you can see, oh, it's going to select RAM. RAM select, this wire is connected to the select line of RAM, which means, hey, RAM, I'm talking to you, pay attention. It is also going to specify the address line. It's going to tell the program counter to specify the address line. So in other words, what it will do is it will turn this mux on. It will use address mux to specify that this mux would use the program counter as the input and then specify the output as the address line on the other side. Okay? It would also specify a few things. It will also specify that we want to store whatever is coming back into the register, instruction register. So you would see this wire turn on. This wire does not have a name. It's just bit 0 of the output. Now this is easy to see. The other bits may require some conversion, but it is very easy to see that bit 0 is going to be a 1 because the hexadecimal number itself ends with a 7. And 7 is an odd number. And as an odd number, bit 0 has to be on, has to be a 1. Okay? So we know we are storing something back into the register. We also know this is going to be a read operation because we are reading 1 byte from RAM. Because when you look at RAM load, which is this Y here, which goes into the load signal or the load port of RAM, it is specifying a 1. And when LD is a 1, we are specifying a read operation. So by decoding these numbers, okay, in the ROM, you can actually tell what is going to happen. And then when you clock it, when you do a Control T to actually clock the processor, then you can actually confirm, oh, okay, I can see that this is exactly what is happening. Okay? So when I clock it, we can expect 8.1 to be stored in the instruction register, which is this one here. And that will basically be fed into here. So microcode pointer should become what? The instruction itself is 8.1, but that specifies the most significant 8 bits. The least significant 4 bits are always going to be a 0. So if 8.1 specifies the most significant 8 bits as a 3 hexadecimal number or as a 12-bit number, what is it going to look like? 810. Okay, so we kind of know what is going to happen next. So we'll go ahead and take a look. Control T and Control T again because we have to look at the clocks. So in one clock, we can see that 8.1 is now stored in the register, instruction register, but we are not quite done with microcode pointer yet because we have not specified to update this one. So now we have another clock. And you can see, now this one is kind of significant because you can see how in the ROM, in the microcode ROM, we are now starting at location 810. And also the microcode pointer itself is also indicating 810. In other words, now we are actually specifying what to do with the add instruction. Now, because yeah, go ahead.
So your assembler instructions are specific to this process that you made?
Yes.
All right.
Well, it's only a toy.
How many different operations after it?
It's only a toy, but it's completely transparent. That's the nice thing about this thing is it runs in LogicSim, only making use of components that we know. Okay, what kind of components are we talking about? Registers, gates, splitters, wires, tunnels. The most complicated devices that we have in this picture, well, okay, a few of those, are the muxes, the demuxes, and the memory modules. But even those are not super duper complicated by themselves. Yep.
So I guess when you're developing a chip or processor, you have to make sure the instructions line up with the operating system that you're working
It's the other way around.
It's operating.
That's a very good question. We got 5 minutes left, but I think this leads to a very good discussion. Okay, so how many architectures, how many processors do you think Linux supports? We'll just pick one distro. We'll pick the Debian distribution. In other words, what I'm asking is, can I run Linux on a machine that has a 386 processor? Sure. What about i5? Yeah, but those are really closely connected. It's the same family, right? What about the ARM chip, ARM ARM chip, which is in your smartwatches, your cell phones, and whatnot? Well, Android is based on Linux, and Linux runs on ARM chips. So we'll go take a quick look. Okay, so we'll take a look at the Debian website, and what we'll do is we'll just look up one particular package that has to be everywhere, and then we can see the architecture supported by that. Oh, that's not what I want. I want to go to Debian packages. There we go. Search over here. Look for Perl. Okay. So here is Perl. You can already see the number of architectures supported. So these are the architectures that are supported. AMD 64, interestingly, is the 64-bit instruction set that is supported by both AMD and Intel. But it's called AMD 64 because AMD got it first. Intel had its own 64-bit instruction set, which is known as IA64. But it was so obscure and so difficult to use that even Intel later on decided, oh, okay, AMD has got a better instruction set. Let's borrow them. So that's why it's called AMD 64. Even your Intel processors make use of the AMD 64 instruction set. So that's your typical desktop computer, laptop computer. You have ARM 64, ARM EL, ARM HF, i386 for older PCs, MIPS, PowerPC, S390X. That's a IBM mainframe computer. Okay, so Linux supports these architectures, or I should say the Debian distro supports these particular architectures. There are graduate school projects where the graduate students are designing a new processor, right? And it's not binary compatible. In other words, the opcode does not resemble any one of these known architectures. And they can get it running in simulation, running Linux. Because they only have to port GCC, the compiler, and everything else, because most of the code of the Linux operating system as well as the utility programs, most of those are written in what? C, C++. So once you retarget GCC to target the new architecture, most programs can just be recompiled and executed. Okay? By comparison, we got 1 minute to point out the contrast of all of this stuff here. How many platforms or how many architectures do you think Windows can run on? Well, it has got 2, okay, because it supports the Intel processor. It also supports the ARM processor to a certain extent. Okay, otherwise you won't have those Windows phones, right? Because you cannot put an i7 into a phone and expect it to be this thin and last the whole day. It can be this thin, but it won't last. It will only last 10 seconds. And you don't want to hold it either because it gets pretty hot. Yeah.
I was thinking for Windows though, if you're doing Windows on a smartphone, don't you have that? Isn't it like a more scaled down, like I guess like not even the whole version of Windows with the smartphone?
I do not know how Windows on the phone compares to Windows on the PC in terms of features, but I would assume it is about the same. Now, when you look at Linux, if you run Linux on the PC and run Linux on a Raspberry Pi, it really is the same Linux. It's the same Perl. Everything is exactly the same. The execution speed will be different because you have a lot more resources on the PC, but they're really the same thing. The same feel, everything is the same. I'm not sure about Windows, whether they are exactly the same or whether they are really different. That I cannot tell.
Okay.
But kind of think about this question, okay? Why is there such a big difference? Okay, why is Linux running on so many different platforms, but Windows only runs on like 2 platforms out of these many platforms? So that's a good question to ask. I will be over at the lab. I do not have a homework assignment for you guys because we're just getting into the processor and I'm still in the process of explaining. So there's no homework assignment. You guys have a long weekend. But I will be over at the lab in case you have questions about what we just talked about today.